In this video, I'm going to continue talking about conjugated systems, and in particular, I'm going to discuss the reactions of allylic cations and thermodynamic and kinetic reactions. So conjugated compounds undergo a variety of reactions which involve intermediates that retain some of the resonance stabilization of the conjugated system. Common intermediates include what are called allylic systems, particularly allylic cations and radicals. So allylic cations and radicals are stabilized by delocalization, or what we oftentimes call resonance. So when we're talking about allylic positions, we're talking about this carbon that is one single bond away from this double bond right here. So we can have allylic bromide, so this bromide is on this allylic carbon right here. We can have allylic alcohol, so this alcohol is on the allylic carbon right there, and allyl benzene, where we have this benzene on the allylic carbon right there. And so if we talk about allylic bromide, when it's heated with a good ionizing solvent, so something that can stabilize the bromide ion, it ionizes to the allyl cation. So more substituted analogs are called allylic cations. So allylic cations are stabilized by resonance with the adjacent double bond, which delocalizes the positive charge over the two carbons. And so the allylic is right here as far as stabilization between secondary and tertiary carbons. So what's happening is we have this bromide leave right here so that this becomes a carbocation right there, and so we can have stabilization as this double bond can move back and forth between there. And if we have substituted allylic cations, we can have major and minor resonance forms. So if we have this, for instance, we have the positive charge on a secondary carbon. This double bond moves over here, and so we end up with the positive charge on a primary carbon. And so the secondary is going to be the major resonance structure. We can do the same thing down here. So again, we have this double bond moving over here, and this tertiary carbon is going to be the major carbocation resonance structure there. And we can have this in a ring as well, where we have this moving here. Since this is equally substituted on either of those carbocations, there is no major one there. But if we put some substituents on here, so say putting a methyl group there, we could get major resonance forms as well. And so when we have these allylic carbocations that result from the addition of HBr here, so what we're doing is we're taking this double bond, we have it going and grabbing that H plus right there, the electrons go to bromide, so we end up with this right here. So we can have this product right here or this one right here. And so this bromide could then attack either at this secondary carbon right here or at this primary carbon right there. And so what we see are two different types of products here. So we can have the 1,2 addition right here, where this hydrogen adds to the 1, the bromide to the 2 position right there, or the 1,4 addition, where the hydrogen adds to this one, and this bromide adds 4 over right there. And so we can get two of these different products here, and we want to know how to predict which of those products we can get. And so this is where we come in with the kinetic and thermodynamic control of HBr addition to 1,3-butadiene. So we see that temperature has an important effect on the products in the addition of HBr to 1,3-butadiene. If the reagents react briefly at -80 degrees Celsius, the 1,2 addition predominates. If the reaction is later allowed to warm to 40 degrees Celsius, or the original reaction is carried out in 40 degrees Celsius, the 1,4 addition is favored. So we see something like this, where we are adding this HBr to this double bond right here, and the bromide could go to the 2 or the 4 position. And if we do it at this very cold temperature here, then what we will see is the 1,2 product is major. So that'll be about 80% here. And if we then let it warm to 40 degrees, or we carry it out at 40 degrees, we actually see that the 1,4 product is going to be the major one here, so 85%. And so the reason for this is because we have the stabilization of the transition state when we are at colder temperatures. So the 1,2 addition occurs when the bromide attacks the secondary carbocation. So the secondary carbocation is going to be more stable, and so it has this lower transition state energy here. And so that means we end up with the 1,2 product forming faster. But when we think about the stability of the product itself, having this internal double bond is more stable. So we want to get the Zaitsev product where we have more substitution on the double bond. And so although this transition state is higher in energy because we have to add to a primary carbocation rather than a secondary carbocation, the product itself is actually more stable because that is the Zaitsev product. So we have a higher activation energy, but we have a lower energy product right here. And so the 1,2 addition has lower activation energy and so reacts faster. This is because it is on a more substituted carbocation, reducing the energy of the transition state. Since this is an exothermic reaction, the reverse reaction is very unlikely to occur at cold temperatures. So when we're at cold temperatures, this is still exothermic right here. So we kind of go over this hill down to here. Then at cold temperatures, we are unable to get back over the hill right there. And so it traps it at that product right there. So the 1,4 addition is even more thermodynamically favored. It is even more exothermic because, as I said, it is Zaitsev. It has the more substituted double bond. So any 1,4 addition product that forms is unlikely to go through the reverse reaction, even at higher temperatures. So we're trapped even further down in this valley here. Even at higher temperatures, it would be difficult to get back over that peak right there. At 40 degrees Celsius, the reverse reaction from the 1,2 addition can occur. So when we heat it up, we are able to actually get back over this right here, and we will be in equilibrium going back and forth right here. But we can get back over here, and then the ones that kind of go back over this hill here instead will get trapped down there. And so we end up with more of that product getting trapped there. And so it will keep getting trapped there and end up with that as the predominant product. So what we see is this reaction here. So this is our 1,2 product here. This K1 is faster than this K2, so we are going to form a rapid equilibrium with this 1,2 product here because this K-1 is also quite large. And so we're going to have a rapid equilibrium between the 1,2 product and this reactant here. But then once this goes this way, we end up with this right here. And since K-2 going back to the product is very small, we end up with that product being trapped. And so what we see is at time 0, so before the reaction, we have 100% reactant here. But then at some time t1 here, we will have mostly the 1,2 product. But then at some time t2 here, this product will start going down while this one is going up, and we're getting trapped in that 1,4 addition. Then at time t3, we end up with this at about 0.75, so about 75%. And this has gone down, so at T3 right here. And we can look at the graph like this as well, where we are looking at time t equals 0 here. We are at all reactants. We allow the reaction to occur. At t1, we now have mostly the 1,2 addition right here, while the 1,4 addition is steadily going up. And so we end up with some of the reactants getting reproduced here as the back reaction from the 1,2 addition is occurring, but the 1,4 addition product keeps going up because we don't get as much back reaction. So by the time we get here, a lot of our 1,2 addition has gone back to reactants, which then moves towards products. And so we end up getting more and more product forming here. So we end up with more of the 1,4 addition. And so we can think about this in terms of the equilibrium here as a function of the rate constants. So our 1,2 addition, we have K1 over K-1, so that's our equilibrium right here. And then for the 1,4, we have K2 over K negative 2. That's our equilibrium right here. And we see that since K1 is greater than K2, this does have a larger numerator than this one, but then K negative 1 is also a lot larger than K negative 2, so this also has a much larger denominator. And so our KEQ for 1,2 addition is going to be smaller than our KEQ for the 1,4 addition. And so we can think of controlling our reaction, which product we get, by controlling the temperature at which we do this, and then we can use Le Chatelier's principle. So say we want to get the kinetic product, so what we would want to do is form it this way at a low temperature, then somehow remove the product, maybe through some sort of distillation, so that we just keep pushing the reaction towards the kinetic product there. And so this is a way, as I said, that we can control the reaction. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.